next step is to develop the concepts of motion. And along the way, we bump into the creation of calculus. It's no coincidence that Newton invented calculus and physics almost simultaneously. The first motion term we're going to define is velocity. Velocity includes both the magnitude, and the magnitude of velocity is usually referred to as speed, as well as the direction of motion. So velocity is a vector quantity. Speed, specifically average speed, is distance traveled per unit time. And you're familiar with this. You see this on signs by the side of the road all the time. You're going 50 miles per hour. So your maximum allowed speed would be 50 miles per hour. The amount of distance that you travel divided by the time that you travel it is your average speed. So if it takes you 2 hours to go 30 miles, you're going 15 miles an hour. The instantaneous speed is the speed at an instant. But this is an interesting concept because if you think about it, you cannot measure that directly. You can approximate it by using increasingly small durations, but the concept of speed at an instant, or instantaneous speed, is a mathematical construct. It's not a real thing in the sense that it's a number that can be measured. So we have two location vectors here, Ri and Rf. The displacement between the initial point and the final point is given by this Rf minus Ri, or Rf plus negative Ri. And so the velocity vector is that change in position, the R2 minus R1, or Rf minus Ri, divided by the time. The direction comes from the distance traveled along the x-axis, R2x minus R1x, the distance along the y-axis, R2y minus R1y, and the distance along the z-axis, R2z minus R1z, each individually divided by the time. Notice this is the bracket notation that we introduced in the section on unit vectors, where the I, j, and k are assumed, and we write the vector as a combination of x part, y part, z part inside the bracket. So the velocity vector v, or the average velocity vector v, is delta r over delta t. Now, if we were looking for instantaneous velocity, we would have to have the value at a specific instant. But it's not a direct measurable because v, by its nature, has a time interval and a space interval, what we call a displacement, a space interval, and a passage of time. So you cannot have a zero passage of time and still have motion. So the instantaneous velocity is not directly measurable. But let's think about this a little bit. Velocity, duration divided by, or displacement divided by duration. And the duration cannot be zero. So the idea of a velocity measurement at a single specific time really provides no information. So we have to solve this problem in a different way. So let's think about how we could improve our measurement. We could decrease our time interval. We could get a better watch. We could use a radar pulse, which would would be limited by the rate that we can generate pulses. So we could have a much finer measurement that way. We could use the Doppler effect, which is a change in wavelength as a result of bouncing off a moving object and having the new object change the wavelength, but that's limited by the period of the light wave. So we could use light with a shorter period, a higher frequency. We could use X-rays or gamma rays or whatever. But ultimately, you always have a duration. So at least in principle, you could make that duration as small as you wanted to make it. But you could never truly make that duration of your measurement zero. So the instantaneous velocity by itself is really a sort of impossible concept. So let's work with this example. We want the instantaneous velocity at time equals t1. We have our t-axis along the horizontal. We have our position axis along the vertical, in this case, x. So we have our point t1 here, but we can't measure the value at t1. We can only measure durations. So we could pick 2 points, t1 minus some time and t1 plus some time, and that would give us a duration over which we could make our measurement. So in this case, at x1 plus x is 5, at x1 minus, corresponding to t1 minus t, the x is 3. So we have 5 minus 3 in the numerator. We would have 6 minus 2 in the denominator. So whatever our length unit is, divided by whatever our time unit is, we would have 2 over 4, or 1/2, and we would have an average velocity for that stretch equal to 1/2. Another way of thinking about this is we could connect the 2 points with a line. And when you connect 2 points along a curve with a line, it's called a secant line. And the slope of that line, if you think about it, is the velocity that we calculated on the previous page. Delta x would be the vertical change, and delta t would be the horizontal change. So pause here and convince yourself that this is true. Really think about it. Seriously, really think about it. Make it an important part of you because it's a key piece of understanding. If you get the idea that this slope, the slope of this secant line, gives you an average velocity over this interval, and then is going to in some way be approximately the velocity for t1, you'll go a long way towards understanding a lot of very important concepts. Because we could now make our t smaller, so that our 2 points are closer in time to t1. And now we get a different answer. And visually, if you think about the previous page and you think about this page, this answer is probably closer to right, because before we were flopped way down here. Much less likely to give us a better answer. So we move closer, and we get something that's probably a little bit closer to right. Now, in your mind, you can move those 2 points closer to the middle point. And then you can move those 2 points closer to the middle point. And then you can move those 2 points closer to the middle point. And you keep going, and you keep going, and you keep going, and you keep going. And ultimately, you can go as far as you want. You could go forever if it was interesting enough and if you were going to live long enough. But you can imagine what would happen as you go on forever. Those 2 points get closer and closer and closer. So the secant lines that are getting closer and closer to the point that we're interested in is what's called taking the limit. And if you are currently taking calculus, you will have not quite seen this yet, but you'll see it very soon. So you'll have a little bit of a leg up here because you'll actually understand this process quite well. The secant line, which intersects at 2 points locally, is approaching the tangent line, intersecting at 1 point locally. So the slope of the secant line is the average velocity, the rate of change. So we can call the slope of the tangent line the instantaneous velocity. And we now have a process, at least in imagining, to find that. So what we need is to actually expand that so that we can do it in a more general case and actually get an answer. But this is half of calculus. This is half of the understanding of calculus, is the conversion from these thinking about the approximate secant line to thinking about how the tangent line is actually going to form. So next, we will look at this in a slightly different way.